This screencast video attempts to show you how to use Microsoft Excel, specifically a app that I wrote in Microsoft Excel that will produce those confidence intervals for the population means, which is material hailing from section 7.2. And it will either use the T distribution or Z distribution based on if sigma is unknown, which is the norm, or the rare case where sigma is known. So the first example on the worksheet was dealing with the lengths of metal screws, where the average given was 4.8 centimeters, and the standard deviation of the sample of 30 screws that were sampled was 0.4 centimeters, and the confidence level was 95%. And using the T critical value from the table, I believe it was 2.045, but this is a more accurate value using the T inverse functionality in Excel, and it computes the error using the formula, the critical T value multiplied by the sample standard deviation divided by the square root of the sample size, and then rounds that to the closest hundredth, and then adds and subtracts it from the sample mean, which was to the closest tenth. So that produced the lower and upper bounds of 4.65 and 4.95 respectively. Example 2 dealt with sensory rates for patients who had undergone acupuncture, and the data was given instead of sample statistics. So this means that you had to first find the mean and the standard deviation from that sample, and then use them here for where, instead of having them being provided, you are going to put them right here and here in my little app I've created. And the sample size you have to put here, and followed by the proper confidence interval. So the mean, I'm not sure what units these are for, sensory units, sensory rates, but the average value was 8.22 with a sample standard deviation of 1.67 from a sample size of 15, meaning the degrees of freedom is 14. We saw how to use a table to look up the area in two tails of 2%, which is the significance level associated with the 98% confidence level. And I believe the exact T critical value is 2.624 from the table, but this, using the T inverse functionality, finds an even more accurate version of it. Once again, using the error formula, T critical value times sample standard deviation divided by the square root of the sample size yields an error of 1.13, and when added and subtracted to the mean value, we get the upper and lower bounds respectively for the sample standard deviation. And those are, as long as you put in these values here or the data and it finds those means and then you put them in here, it'll automatically find the lower and upper bounds of the confidence interval. In the rare situation where sigma is known, again, we are creating a confidence interval for a population mean. That means we don't know the population mean, so we probably do not know the population standard deviation. But in the rare case that we are creating a confidence interval for an unknown population mean, when somehow we know the population standard deviation, we use sigma instead of the sample standard deviation. So the example given was birth weights of females in hectograms, where apparently the population standard deviation is 2.9 hectograms. The sample size of 15 birth weights, we do not need to find the degrees of freedom because we know sigma. We're going to use the normal distribution and critical Z values. And this goes back to using the norm inverse functionality. And once you describe the proper confidence level, it will compute a more accurate value than you would see for the table for the critical Z value. And then using the formula where the critical Z value times the population proportion divided by the square root of n computes the error, and when you add and subtract that error from and to the mean, you get the lower and upper bounds of the confidence interval for the population mean. So moving on to the examples from the You Try It portion of the worksheet. So You Try It number 1 was talking about the mean hours that students watched TV, and in order to have this formatted so that a problem where data was performed, I needed to put it in the middle here. So notice that this is the app being used for example 1, not number 2, that comes second, and the app here has the work for solving example 2, not number 1. So these are the 15 different number of hours that students said they watched TV weekly, which had an average of 6.13 with a standard deviation of 5.51. On the worksheet key, it only says 6.1 and 5.5. So I'm using slightly more accurate values. So you'll see the answer deviates a tad bit from the answers on the worksheet, just because I'm using a more accurate value for both the mean and the standard deviation of the sample. When data is given, we're assuming again that sigma is unknown. So we're back to using the t-critical value, and the t-inverse value used to find the error computes an error of 3.05. And when you add and subtract that to the more accurate version of x bar, the sample mean, we get 3.08 and 9.18, which is not the 3.05 and 9.15 that you see on the worksheet key. Going to example number 2 is this first problem over here on the left, and that dealt with the number of hours of sleep per night that patients were able to achieve after having hypnotherapy. And the average hours of sleep were given were 8.98, almost 9 hours of sleep a night. Wow. Maybe I need to get some hypnotherapy. The standard deviation of that sample was 1.29 hours. There were 12 people in that study. Because sigma is not known, we're back to using the t distribution, the t student distribution. So we need to know the degrees of freedom. And I'm betting that the chart probably says 3.106 to the closest thousandth. But this, again, finds a more accurate value for the t critical value based on a 99% confidence interval. When the error is computed via the formula we've seen before, using the t-critical value and the sample standard deviation, the error was 1.16. So when you add and subtract that to the sample mean, you get the upper bound of 10.14 and lower bound of 7.82, which this app will automatically do for you as you change these values per problem that you're working on. Last example was yet another example of where we were dealing with birth weights of females, but instead of 30.9 being the average of a sample of 12 birth weights of females, the average was a little bit higher. It was 31.1, and that was coming from a sample of 22 birth weights for female. We're still using the same sigma value of 2.9. The confidence level indicated in this problem was 95%. This is the critical z value more accurately using the inverse norm functionality in Excel. And I simply routed this error to only the closest tenth, so I could add and subtract it to the given sample mean to get the lower and upper bounds of the interval. So this is a nice little app that you can use instead of StatCrunch or the graphing calculator to find the confidence intervals for population means, either using the t distribution, which is most often used, or the lesser used z distribution. All right, take care.